So today we shall discuss primitive roots mod p. P is a prime number, and for any prime p the primitive roots always exist. We can assume that even p is odd prime. If p is equal to 2, phi of 2, that is 1, and we want an element of order 1, and 1 is an element of order 1. So we can say 1 is a primitive root mod p. So let us recall that primitive root means an element of order phi of m is called a primitive root mod m. If m is prime, then an element of order p minus 1 will be called a primitive root. Element A is called a primitive root mod p prime if order of A mod p is p minus 1. Is p minus 1. Because phi of p is p minus 1. So if we have an element of order p minus 1, it's called a primitive root. And we will show that such an element always exists. So we shall have the following lemma. If Q is a prime, such that Q raised to A divides p minus 1, where p is also assumed to be prime. Then there is always a residue class whose order is Q raised to A. And we can say how many are there of this type. Then there are Q raised to A minus Q raised to A minus 1. Residue classes B mod P. That many values of B are there of order Q raised to A. There are exactly this many residue classes B mod P of order Q raised to A. So this is for all primes Q which divide p minus 1. Proof of this depends upon the result that we have seen earlier. The number of solutions of x raised to q raised to a minus 1 congruent to 0 mod p. Consider this d, x raised to d minus 1 congruent to 0 mod p. We have seen that if this d divides p minus 1, then there are d solutions, d equal to q raised to a here, solutions to this congruence. Is q raised to a provided q raised to a divides p minus 1, and here this condition is satisfied. Usually for a polynomial congruence, number of solutions is less than or equal to the degree of the congruence. But in this case, when d is a divisor of p minus 1, the congruence has d solutions. Now, these are the elements, q raised to a elements are there, whose order divides this q raised to a. Okay. X raised to d minus 1 congruent to 0 mod p. Some element satisfies such a congruence equation. If that element is b, then order of b will divide that number d. Okay. What is the meaning of an element of order q raised to a? We want to find out number of elements of order q raised to a. So b is such an element, means b raised to this power q raised to a should be congruent to 1 mod p, but no lower power. Okay. Now a lower power, if it is there, what will that be? That if the order of that element is smaller than q raised to a, and that element satisfies b raised to q raised to a is congruent to 1 mod p, then order will be a divisor of q raised to a. So note that b has, so b mod m, here m is p, has order q raised to a if 1 b raised to q raised to a is congruent to 1 mod p, and no lower order should be possible. What does that mean? if some lower order is there, then that has to divide q raised to a. So it will be 1q, q square, etc. some power. Lower means it should be up to q raised to a minus 1. If any of these 1q, q square, etc. is an order, then it would mean that b raised to q raised to a minus 1 will be congruent to 1 mod p. And that should not happen. That is the second condition. B raised to q raised to a minus 1, that is not congruent to 1 mod p. B mod p has order q raised to a, means first condition b raised to q raised to a should be congruent to 1 mod p. Second condition, order should not be smaller than this. But if order is smaller, then it has to be a divisor of q raised to a. It is a proper divisor. Proper divisor means 1q, q square up to q raised to a minus 1, one of these. Order must be one of these. If order is any one of these, then b raised to q raised to a minus 1 would be congruent to 1 mod p, which we don't want. So it is not congruent to 1 mod p. So these are two conditions for order of b to be q raised to a. Okay? This is a small important observation. Order of an element is a power of q provided that element raised to this q raised to a power is 1 and no slightly previous power q raised to a minus 1. We shall do a lemma based on this later on for general order. So that means it is a solution to the congruence x raised to q raised to a minus 1 congruent to 0 mod p. So in other words, b mod p has order q raised to a if and only if b mod p is a solution to x raised to q raised to a congruent to 1 mod p, but not a solution to the congruence x raised to q raised to a minus 1 congruent to 1 mod p. This is the first congruence, this is the second congruence. How many solutions are there for this congruence? We are assuming that q raised to a divides p minus 1. Under this condition, this congruence has q raised to a solutions equal to the degree, that many. That means there are this many q raised to eighth roots of unity available mod p. So since q raised to a divides p minus 1, one has q raised to a solutions. Note that any solution of 2 is the solution of 1. Okay? Because you take a solution of this, raise it to qth power, you get a raised to q raised to a congruent to 1 mod p. So solutions of this are also solutions of this. How many solutions are there for 2? Again, q raised to a itself is dividing p minus 1, therefore this lower power q raised to a minus 1 is also going to divide p minus 1. Since q raised to a divides p minus 1, q raised to a minus 1 also divides p minus 1. Therefore, 2 has q raised to a minus 1 solutions. Now we want solutions of 1 which are not solutions of 2. But see that all solutions of 2 are here and solutions of 1, so solutions of 2 are subset of this. It's going outside. So elements which satisfy 1 but do not satisfy 2, such residual classes we want. B is a solution to first but not a solution to second. So such residual classes are q raised to a minus q raised to a minus 1 in number. Residue classes or elements from any reduced residue system which are solutions of 1 but not of 2 are how many? Q raised to a minus q raised to a minus 1 in number. And all such elements are of order q raised to a. All such residue classes are of order q raised to a. So number of residue classes of order q raised to a is q raised to a minus q raised to a minus 1 in the case when q raised to a divides p minus 1. So if q raised to a divides p minus 1, there is at least one element of order q raised to a, and in fact these many elements are there of order q raised to a, and this is what we shall use to show that primitive roots exist mod p. So this is a very important theorem about residue classes mod p. There are phi of p minus 1 primitive roots mod p. Proof. So basically this is for p bigger equal 3, p equal to 2, this is obvious. P equal to 2 means phi of 1, that is 1. That many primitive roots mod 2 are there. 1 is the only primitive root mod 2. Okay. Now you take, so if p equal to 2, p minus 1 is 1, phi 1 is 1, and there is exactly one probability root mod 2, namely 1. 1 is the probability root mod 2. That's the only one, mod 2. If P is bigger than 2, that is P bigger equal 3 odd prime, then P minus 1 is bigger equal 2, and you can factorize P minus 1 as a product of prime powers, right? P minus 1 equal to Q1 raised to A1, Q2 raised to A2, etc. QR raised to AR. This is canonical factorization. So QI distinct primes and AI bigger equal 1. AI bigger equal 1. Now, Qi raised to Ai, that's a factor of P minus 1. Therefore, we can find many elements of order Qi raised to Ai. How many? Qi raised to Ai minus Qi raised to Ai minus 1. That many elements you can get whose order is Qi raised to Ai. So, you get at least one. That's the point. So, since Qi raised to Ai divides P minus 1, there is a residue clause B mod P of order Qi raised to, so let us call this as Bi mod P, Bi mod P of order Qi raised to Ai. At least one is there whose order is Qi raised to Ai. Now, Q1 raised to A1 and Q2 raised to A2, they are co-prime. Therefore, if I take B1, which is of order Q1 raised to A1, and B2 of order Q2 raised to A2, then their product B1, B2 will be of order Q1 raised to A1 into Q2 raised to A2. Then you can have some B3 like that. So you take these B3, B1, B2, B3 and so on, take their product, and that is going to be of order Q1 raised to A1, Q2 raised to A2, etc. Okay. So this result that if A is of order H and B is of order K mod M and H and K are co-prime, then what is the order of AB? It's equal to the product of orders H into K. That's what we have to use again and again. So since Q1 raised to A1 etc. QR raised to AR are co-prime in pairs and Bi mod P has order Qi raised to Ai. The product B equal to B1, B2, Br is of order Q1 raised to A1 etc. QR raised to AR. But what is this? This is exactly P minus 1. So we have got an element B such that order of B mod P is P minus 1. So we are using the factorization of P minus 1 in this. That P minus 1 is Q1 raised to A1 etc. So B is of order this product, that's P minus 1. Thus, there is a residue class B mod P of order P minus 1, and so B is a primitive root mod P. Now how many primitive roots are there mod P? Number of primitive roots mod P means number of distinct elements, incongruent elements mod P whose order is P minus 1. Now note that, so take any primitive root mod P. Many times such a primitive root is denoted by G, by the letter G. So take any primitive root, let G be any primitive root mod P. Okay. For example, B was constructed and it was a primitive root mod P. So take any such. Now take powers of this G. So note that G raised to 1, G raised to 2, etc. G raised to P minus 1, that's congruent to 1, this is congruent to 1 mod P, are distinct mod P. They are distinct mod P. They are incongruent mod P. Why are they incongruent? Suppose two of them are congruent. For suppose G raised to I is congruent to G raised to J mod P for, so one of them is smaller, let us say I is smaller than J, 1 less than or equal to I less than J less than or equal to P minus 1. Then you can cancel G raised to I from both sides because it is coprime to P. See that G raised to P minus 1 is congruent to 1 mod P. G is primitive root, so its order is P minus 1. It must be coprime to P. So we can cancel G raised to I and get G raised to J minus I congruent to 1 mod P, where J minus I is bigger than 0 and it is less than p minus 1 because j is at most p minus 1 and you are subtracting at least 1. I is bigger or equal 1. You are subtracting I. So it becomes less than p minus 1. So the smaller power of g becomes 1. It's a positive power which is 1 and it is smaller than p minus 1. So this contradicts that order of g is p minus 1. That order of g mod p is p minus 1. This contradicts that the order of g mod p is p minus 1. That means these elements must be distinct mod p. Now, one, two, etc. p minus 1 are p minus 1 incongruent elements mod p and these are coprime to p. Coprime to p. G square etc. g raised to p minus 1, they are also incongruent mod p. They are also p minus 1 in number and therefore they must be a permutation of 1 to etc. p minus 1 mod p are coprime to p and incongruent mod p. Hence they are a permutation of 1 to etc. up to p minus 1 mod p. We can say that they form a reduced residue system mod p. In other words, g square etc. g raised to p minus 1 form a reduced residue system mod p. Any element congruent to, not congruent to 1 mod p, any element which is coprime to p must be congruent to one of these. Any integer coprime to p must be congruent to one of these mod p. Whether you take a number from 1 to p minus 1 or any element of a reduced residue system mod p, it has to be one of these. Now, we are reduced to finding elements of order p minus 1 from this set, because this is a reduced residue system. To find residue classes mod p of order p minus 1, we should find k such that order of g raised to k mod p is p minus 1. But what is order of g raised to k? That is, order of g is p minus 1. P minus 1 by k p minus 1 is p minus 1. We have seen that order of g raised to k is order of g divided by GCD of k and order of g, that is p minus 1. This should be p minus 1. Now if this you want to be p minus 1, what should be this number? This number must be 1. If it is bigger than 1, then this will be smaller than p minus 1. So that is k p minus 1 equal to 1. Hence, the number of k such that order of g raised to k is p minus 1 is the number of k such that, so we are assuming of course 1 less than equal to k less than equal to p minus 1 and k p minus 1 is 1. GCD of k with p minus 1 is 1. How many k are there? The number of such k is denoted by phi of p minus 1. Number of such k is denoted by phi of p minus 1. Now, primitive root means an element of order p minus 1. So, number of primitive roots is phi of p minus 1. That many elements of order p minus 1 are there. Therefore, number of primitive roots mod p is phi of p minus 1. Phi is the Euler's function. Let us find, for example, find all primitive roots mod 13. Thirteen is a prime number, so there is going to be a primitive root, and the number of primitive roots is expected to be phi of 13 minus 1. Okay, so here p equal to 13, so p minus 1 is 12, phi of p minus 1 equal to phi of 12. And phi of 12 is phi of 4 into phi of 3. Phi is multiplicative. Euler's function is multiplicative. 4 into 3. 4 and 3 are co-prime. What is phi of 4? That is 2. Phi of 3 is 2. That is 4. So there are going to be 4 primitive roots. Hence there are 4 primitive roots mod 13. You should find at least one, and from that you find others. So try with 2. 2 raised to 1 is 2. 4, 8, 16 means 3. This is mod 13. 2 raised to 5 is 6. Mod 13. 2 raised to 6 is 12. Mod 13. 12 is minus 1. Okay. This is congruent to 6. Congruent to 12 is minus 1. So this shows that order of 2 must be 12. Because after this 2 raised to 7, 2 raised to 8, they are going to be negatives of this. 2 raised to 7 is minus of 2, minus 4, minus 8, minus 16, minus 6. And 2 raised to 12 is plus 1. So order of 2 mod 13 is 12. So 2 is a primitive root. Mod 13. Now if you know one primitive root, it is not necessary to find out now 3, whether 3 is a primitive root, 4 is, etc. You just take powers of this, and from that you get other primitive roots. So other primitive roots mod 13 are they are 2 is one primitive root, so 2 raised to k such that k 12 equal to 1. You take 1 less than equal to k less than equal to 12 and k 12 equal to 1, out of which k equal to 1 you have already taken, 2 raised to 1. So others you have to find out. So what are the values of k which are co-prime to 12? They are, so you should take 5, 7, 11. So 1 is there which I already considered, and these are remaining 3, 5, 7, 11. So what is 2 raised to 5? Therefore 2 raised to 5, which is congruent to 6 mod 13, 2 raised to 7, which is congruent to minus 2 mod 13, or we can say 11 mod 13, and 2 raised to 11, which is congruent to minus 6 mod 13. They are primitive roots. Are primitive roots. In one stroke, we could get all primitive roots mod 13. If you want the standard way of writing the primitive roots, then you can write 2, 6, then this is 11 and this is 7. So this 2, 6, 11 and 7 are all the primitive roots mod 13. They are all the 4. As I said, primitive roots are there for non-prime values also, and we have taken 10 as an example. So 10 is not a prime number, it is 2 times a prime number, and that also has a primitive root. In that case also, in a similar fashion, we can find out all primitive roots from 1. So if m is a composite number, for which there is a primitive root G mod m, then G raised to 1, G raised to 2, etc., G raised to phi m, which is congruent to 1. So G raised to phi m is 1, and phi m is the order of G, because G is primitive root. And these powers are distinct, are incongruent mod m, and so form a reduced residue system mod m. As we have seen for a prime p, same thing happens, same proof. All of them are distinct or incongruent mod m. Again, any element which is co-prime to m is a power of G. That's the advantage. Once you have primitive root, any element which is co-prime to m is congruent to a power of G. And what is its order? Again, its order is, if the element is G raised to k, the order is phi m by GCD of k and phi m. Again, if b m equal to 1, b is congruent to G raised to k mod m for some k 1 less than equal to k less than equal to phi m. Any element co-prime to m is of the form G raised to k, because these are phi m elements which are incongruent. And therefore, what is the order of B? Is order of G, that is phi of m, divided by k phi m. This is phi m if and only if k phi m equal to 1. The GCD of k and phi m is 1. So how many primitive roots are there? Mod m. Number of primitive roots mod m is number of k such that 1 less than equal to k less than equal to phi m, and k phi m is equal to 1. So that is phi of phi m, okay, because we are comparing with phi m. Therefore, the number of primitive roots mod m is phi of phi m. See, if m is p, then phi of m is p minus 1. Therefore, for a prime p, number of primitive roots is phi of p minus 1. Okay. Of course, here for a composite m, there may not be a primitive root. If there is at least one, so we are assuming that m is a composite number for which there is a primitive root. If there is a primitive root, then the number of primitive roots is phi of phi m. So, how many primitive roots are there? Mod 10, for example. So that is 2. M equal to 10, phi of m. This has a primitive root. For example, 3. 3 is a primitive root. 3 square is 9, that is not 1, mod 10. 3 has order 4. Phi of m is 4. Phi of m is phi of 4, that is 2. So there are 2 primitive roots mod 10. And they are, what are they? 3 is 1, and actually the inverse of 3 will also be of the same order. A and A bar, they have the same order. So inverse of 3 is 7. 3 into 7 is 1. So inverse of 3 is 7 mod 10. So 3 and 7 mod 10. Okay. So this is about primitive roots mod p, that if p is a prime number, primitive root mod p exists, and it is, if one of them is known, you can find out all other primitive roots. It is possible to find out primitive roots mod 2 times p also. So and this primitive root mod 2p, like 10 is 2 times p is prime, p is 5 in this case, 10 is 2 times 5. So in such a case, it is easy to find primitive root mod 10 from primitive root mod 5, or primitive root mod 2p from primitive root mod p. So how do you get that? So suppose, so this is a exercise, you can try it. Suppose A is a primitive root mod p. A is a primitive root mod p. A itself can sometimes be a primitive root mod 2p. But the requirement for that is A should be odd. So if A is odd, then A itself is a primitive root mod 2p. Its order mod 2p should be phi of 2p. What is phi of 2p? I am assuming p odd prime. That's the assumption. That is, A has order phi of 2p, which is the same as phi of p mod 2p. See, order of A mod 2p is p minus 1. If A is even, then A 2p is 2, it's not 1. A is not coprime to 2p. In this case we modify A. Then A1 equal to A plus P is such that A1 2P equal to 1. A is coprime to P, so A1 is also coprime to P. A was even and A was not coprime to 2, but now I have made it odd by adding P to it. A is even, P is odd prime, so A1 is odd. So A1 is now coprime to 2P, and now you can check that A1 is of order phi of 2P, that is P minus 1 modulo 2P. So then order of A1 mod 2P is phi of 2P. Phi of 2P means phi of P, because phi 2P is phi 2 into phi of P, that is phi of P, which is P minus 1. Okay. So order of A1 mod 2P is P minus 1. See here, just take the first part. Suppose A is odd. Then A raised to, so A odd, that case I will just illustrate. What we already have is A raised to P minus 1 is congruent to 1 mod P. This anyway we have, and A raised to P minus 1 is also congruent to 1 mod 2. Therefore A raised to P minus 1 is congruent to 1 mod 2P. Now this you can also get by Fermat's little theorem. So order of A mod 2P, it divides P minus 1. And now you, using that A is the least, such that order of A mod P minus 1 is the least, such that order of A mod P is P minus 1. Here also you show that P minus 1 is the least. Because if for some smaller power, if for some r 1 less than or equal to r less than p minus 1, if it happens that a raised to r congruent to 1 mod 2p, then a raised to r is congruent to 1 mod p also, and then that is not possible because order of a mod p is actually p minus 1. So this is not possible. A raised to r congruent to 1 mod p, this is a contradiction. So no smaller r can work, and therefore order of a mod 2p is also p minus 1, because a raised to p minus 1 is 1 mod 2p. If smaller power is also 1, then same r will work for p also, but that is not possible because order of a mod p is p minus 1. Okay, that proves the result. You can try the other one similarly.